Welcome back to Future Minds, JNA Data Science. I am your host, Manav. I am thrilled to have you join me for our fifth episode. In our previous episodes, we explored the basic neural networks, advanced architectures like CNN, RNN, the power of transformers, and neural networks, advanced architectures like CNN, RNN, and delve into unsupervised learning and its application. Today, we are going to take step further and discuss reinforcement learning and fascinating area of AI that's driving advancements in robotic gameplay and decision making systems. Let's begin. Reinforcement learning or RL is type of machine learning where an agent learns to make decision by interacting with an environment. The goal of agent maximize cumulative reward over time unlike supervised learning where the model is trained on fixed data set. Reinforcement learning involves continuous feedback loop between agent and environment. At the core of reinforcement learning are three key components: the agent, the environment, and reward signal. The agent takes action based on the current state and the environment respond to those actions. Transition to new state. The state receives reward or penalty based on the action taken. This process is often modeled as Markov decision process or MDP, which provides mathematical framework for decision making in stochastic environments. One of the most well-known algorithms in reinforcement learning is Q-learning. Q-learning is value-based method that aims to learn optimal action value function, also known as the Q function. The Q function estimates the expected cumulative reward for taking particular action in given state and following the optimal policy. Thereafter, the action updates its Q value iteratively based on the reward received and the new state encounter. Q-learning is powerful, but it has limitations, especially in environments with large or continuous state space. To address these, researchers develop Deep Q Network or DQN. DQN combines Q-learning with deep neural networks, allowing agents to approximate the Q function using neural networks. This approach was famously applied by DeepMind to achieve superhuman performance in Atari games, where the DQN agent learned to play the games like Breakout, Space Invaders, and indirectly from raw pixel inputs. Another significant advancement in reinforcement learning is the development of policy based methods. Unlike value based methods that estimate the value of action, policy based methods indirectly optimize the policy, which defines the agent behavior. A popular policy based algorithm is reinforcement algorithm, which uses gradient ascent to maximize expected cumulative reward. One of the most successful policy-based method is actor-critic algorithm, which combines strength of based value, both value-based and policy-based approach. Actor-critic algorithm consists of two neural networks: actor, which learns the policy, and the critic, which evaluates the action taken by the actor. By working together, actor critic can improve stability and efficiency of the learning process. Now let's discuss the exciting applications of reinforcement learning. AlphaGo. Developed by DeepMind, AlphaGo is reinforcement learning based on system that defeated the world ca- champion Go player Lee Sedol in 2016. Go in an ancient board game with a vast search space making challenge task of traditional AI approaches. AlphaGo combines deep neural networks with Monte Carlo tree search, a powerful planning algorithm to achieve superhuman performance. A breakthrough demonstrated the potential reinforcement learning to tackle complex real world problems. Reinforcement learning is also making significant strides in robotics by training robotic agents to interact with their environment, and reinforcement learning enables robots to learn tasks like grasping objects, navigating space, and even playing sports. For instance, OpenAI robotic hand and tactile use reinforcement learning to manipulate objects with remarkable dexterity. By learning from simulations and real world interaction, Dactyl can solve complex manipulation tasks that were previously out of reach of for robotic system. In addition, game playing robotics and reinforcement learning is being applied in wide range of domains including healthcare, finance, autonomous driving. In healthcare, reinforcement learning is used to develop personalized treatment plans for learning from patient data and optimizing outcome. In finance, it helps to trading strategies by learning to make decisions based on the market condition. In autonomous driving, and reinforcement learning enables vehicles to navigate complex environments and make real-time decisions to ensure safety and efficiency. Let's bring this back to practical applications. Imagine you are developing a recommendation system for an e-commerce platform. Using reinforcement learning, you can create an agent that learns to recommend products to users based on their interaction with the platform. By continuous updating its policy based on the user feedback, the agent can provide personalized recommendations that maximize user satisfaction and increase sales. Another practical example is in the field of energy management. Reinforcement learning can be used to optimize energy consumption in smart grids, reducing cost and improving efficiency. By learning from historical data and real time conditions, the agent can make decisions on energy distribution, storage, and usage, ensuring balance between supply and demand. To get started with reinforcement learning, you will need to solid understanding of the underlying principles, practical experiences in coding and data analysis. There are plenty of online resources, tutorials, courses that can help you to build these skills, whether you are beginner or experienced practitioner. Libraries like OpenAI Gym provide environments developing testing and reinforcement learning algorithms, while frameworks like TensorFlow, PyTorch offer tools like needed to implement and train these models. Before we wrap up, let's touch some challenge and ethical consideration in reinforcement learning. One of the major challenge is the exploration exploitation trade-off. The agent needs to balance exploring new action to discover their potential reward and exploiting known action that yield high rewards. Striking the right balance is crucial for effective learning. Ethical, ethically, it's important to consider the potential risk, unintended con- consequences of deploying reinforcement learning agent. For instance, an agent trained to maximize profit in financial trading might engage in risky behaviors that could lead to market instability. Ensuring fairness and safety, transparency in reinforcement learning require careful design of rigorous testing of the models and policy. Thank you for joining me today for Future Mind podcast. I hope you found this exploration of reinforcement learning and its application insightful and inspiring. Make sure you subscribe so you don't miss any upcoming episodes where we will continue to dwell into incredible potential of generative AI and data science. Until next time, I'm Manav signing off. Stay curious, stay inspired, keep exploring. Thank you.